expected. I mean, we may bog down in traits here, but it may be that we'll have time for some live coding on Thursday, which is what will happen if we run out of things to talk about with traits and generics. Just show some examples of code at this point. I haven't done as much of that. Probably the 8-week format is just don't have enough time to do all anything that isn't absolutely essential at a given moment. So it's great if we can do that. So in the examples, the first hour, we made heavy use of the into constraint on things, right? And into is interesting because it's not really a type itself, right? It's sort of a constraint on a type that says it has to obey a certain interface. And we call those constraints traits. And they're sort of the fundamental mechanism of sort of, how to say it, of sort of runtime typing in Rust. Rust has a sort of runtime typing, which is sort of notionally associated with these trait things. And so what we're going to do is sort of dive into that, into these interface types. If you've used interfaces in Java, you have a pretty good idea of what's going on. They're also vaguely like classes in an object-oriented language, but they're neither of those things. They're their own thing. They're like Haskell type classes a little bit. They just say, well, you know, it's great that we have this thing where we can say, well, for some specific type that we'll call T, these things happen. Here, what we want to be able to say is, well, you know, there's lots of types that could be a T, and for each of them, they need to provide these things. So the traits are kind of the inverse of generics. They say, well, I'm going to say if something obeys a trait, that means it has to provide, as part of its implementation, the trait operations that you asked for. This is sort of a very important mechanism for code reuse in Rust, and the into is a great example of that, right? Anything that implements the into trait for a type must provide a function into that you can call to turn the, to do the type conversion, right? And that's the thing that's in the standard library, but of course, Rust follows one of the fundamental rules of good programming language design, which is as much as possible, anything that the standard library can do, you should be able to do too. And so we can actually write our own traits. It's a thing. And this is, another way to think of traits as sort of being, how to say this cleanly without getting myself in trouble. By the way, there is an add trait we could use in all those previous examples, but we didn't. We just chose to use i64s for everything. The idea of a trait is that we specify what functions the trait has to implement. What is it? Anybody who implements any type that provides this trait has to implement the trait's methods. And so here we're going to create a new trait for sort of numbery things you can add up. We say, well, something's nubby if the underlying type is addable with itself to produce itself, and then the plus sized here, and we'll talk about what plus sized means later today or tomorrow. So interesting. Now we don't have any generic type names. The only generic type we have is capital self. Now, last week when we talked about structs, we talked about capital self being sort of an alternate name for the type that you're talking about. Well, here, there it was kind of optional. If I'm implementing a struct foo, I can say capital self or I can say capital foo, and they were kind of the same. Here I don't have a name, right? Self in this trait definition refers to the type that the trait is defined over. But I don't know what that is right now, right? I'm just saying, there is some type, we'll call it self, that has these properties. And so as long as self obeys the ability to add itself to itself, then to get, returning itself, then we're going to be able to define a function that actually does the addition. Well, it's kind of a boring function in this case. And then there will be a render function, and the render function returns a self : rendering? Huh? Well, look up at the top. Another thing that traits can do is define generic types. So I'm saying anybody who implements that trait has to provide along with it a definition of its rendering type. That's what's called an associated type. And so, oh yeah, if you're going to have these nummy things, you also have to be able to render the result. And so, by the way, that will produce some rendering type. And I'm going to be agnostic about what that type is. But there will be a render function that will produce the associated rendering type as its result. Well, that's all very abstract. I'm very mystified by this code so far. Let's see what an implementation of nummy actually looks like. We're going to say, well, an F64 is a kind of number. We'll implement nummy for it. Well, what type of rendering do I want to produce? I want to actually produce a string rendering for nummies, it turns out. And what does the render function look like? Well, I'm going to call toString to turn my thing into a string. Yeah? And that's all I need to say. Why don't I have to provide a definition of the add function? Oh, because we provide a default implementation of the add function as part of the trait definition. I really didn't want to do that. As part of the trait definition. And so if I don't provide my own add function as part of the trait implementation, it will use the default one. Clear enough? And so that's very, very common. If you go look at a class like Iterator, which we'll look at next week, Iterator has a ton of default methods. You normally only define a next method for Iterator, and everything else takes the default implementation. But there are all these other functions you can define in different ways if you have a reason to define it in a different way, but otherwise you get the default version, which works. Well, what about number, U64s? Well, it turns out I'm going to take my U64 and render it as a vector of U8s. Why? I don't know, because that's what I want for U64s when I call the render function. And so I'm going to use the default add function again, but my render function here is going to make a new vector and take the digits of the number, push them into that vector, and then flip it around so that I get out actually a vector of the digits of my U64. Fair enough? And so now, after staring at that terrible render code for a minute, we sort of can see that, well, for a floating point number like 1.0, I can render it, and it should print the string representation of that number. It's a very long, roundabout, boring way to get the string representation of the number, right? Here, I can add two U64s using the U64 add function, because there's an implementation of add of nummy for U64. And then I can render that, and I should get a vector out of the digits of 112, I think. So let's see. Not sure why allowing used is even turned on there. I should turn it off and see what it does. And sure enough, 1.0 is a floating point number, renders as 1. Notice that Rust by default doesn't give any decimal digits for floating point numbers that are exact integers. We could argue whether that's a good idea, but it's what the display trait does. And then we get the digits of 112, sure enough. That's good. Yeah? That was very fast. Let's go through that again really slowly. Now that we've got to the end, we can go back and look at the beginning again. Fundamental idea. I can define my own type constraints. I call them traits. In this case, I'm going to have a constraint on a type that says that type is nummy. And you'll now be able to say, oh, something is nummy. Some type is nummy. And you'll be able to say that, sort of, and then you'll be able to use whatever functionality the trait provides. Yeah? So now, and I have a constraint. I can't just make any type nummy. The type has to be addable with itself to produce itself, because that's what the adding operation is going to do. So I've got that little constraint there. And then given that, I have, well, this is what it'll look like when you render it. And this is how you add two things. And there you are. Now, we're going to implement it for a couple types. And then we're going to use it. And notice that the implementer gets to decide what a rendering looks like. The caller doesn't get to decide what a rendering looks like in this case, because there's no, and in fact, really staring at that code again, a better way to write this would be, right, the colon here means just what you think it does, right? This is the type self rendering associated type. And really, I could write it that way, or since I know what that type is, since I know it's string, I could write it the way I originally did, right? Up here, I have to write self : rendering because I don't know what the type is, right? But that type is compatible with this type because this, so we're actually all good. And there again. Okay. Now, an interesting question that you might wonder is, what if, you should never stop asking yourself, what if I wanted to render into a string? Because that's a legitimate thing to want to do. And can I do both? Is that a thing? Let's see what the compiler says. Conflicting implementations. So, doesn't look like it. Oh, so we're gonna have to figure out if there's a way to do that as we go. So, yeah, note the following. The trait bounds, which say what it can be used on, the associated type, the static default method, the default method that's there, the sized marker type, and the use of self. The sized marker type we'll talk about in a minute. And the type inference works. Oh yeah, that's another thing we should say in that example is, notice how much type inference is being done here. There's quite a bit of sort of figuring out that the types are right, that the compiler does for us automatically. So it knows that render produces the right output type and so forth and so on, and you don't have to say too much. Okay, so that's traits. Those are cool. We should probably do more playing around with traits before we walk away from that topic. Having said that, let's talk a little bit about one of the cool things about traits is that, you can use traits as bounds like that, but it turns out you can also make what's called trait objects. Now, trait objects are one of the more confusing Rust topics, but we need to sort them out, so let's do that. Here's an example from the book. which is a really motivating example for this trait objects thing. And the fundamental idea underlying this is, well, let's say something obeys the vegetable trait, right? Well, so far we've made the compiler figure everything out and figure out which kind of vegetable we're talking about at compile time. But why should that be so necessary, right? We know that anything that obeys the vegetable trait, we know there are methods we can call on it. Maybe we should package up the thing along with what's called in C++ a vtable of some kind of indication of, how you call in this case, the description trait on the desk trait, the desk method on that kind of object. Maybe we should be able to have this happen at runtime instead. So I actually have to sort out what kind of vegetable I'm carrying around. So here's the vegetable trait. Here's a couple of implementations of the vegetable trait at various types. Notice we have the empty struct thing again, because this is just a silly example. We have the lettuce struct. We're going to say lettuce is a vegetable. Here's a description. Here's what the description of lettuce should be, right? Oh, tomato is also a vegetable, right? Here's the description of a tomato. It's a tomato. So here's the generic salad. I love this example. Jim came up with a good example. So we've got a generic salad, right? What does a generic salad take? Well, it takes some type which is a vegetable type, right? Which, as far as we know in the whole world right now, the only two vegetable types are lettuce and tomatoes. Yeah. And you can make a generic salad by sticking the veggies into the salad, right? It's a vector of veggies, right? But notice the thing that's going on here, right? This is like our stack example from the first hour. I push a value of type T, right? And I can print the description. This is basically the same code we had first hour, right? Kind of revamped and done with vegetables. What's the funny constraint on my generic salad at this point? Anybody who's read the book this far or just can see it? What's funny about my generic salad done with the generic types here?
It's a salad of one vegetable.
Oh! I can make a salad with as many lettuces as I want in it, or with as many tomatoes as I want in it, but not both at the same time, because the salad, when I create it, it's a salad of a particular type, T, right? I mean, the self here I can absolutely, write as generic salad T, right? Because that's what I'm implementing. Oh, the T is locked in there. It's a particular type, right? That's not good. Now, we talked the first hour about one obvious workaround. What's one obvious workaround for this? Enums, right? And you make an enum vegetable, which might frankly be the right thing to do here, right? That has lettuce and tomato fields, and then instead of all this traits and horrible stuff, right? I can just have a salad struct, right? And it can take vegetables as arguments. But like I said, the problem with that is, I have to keep track, it makes me write a bunch of very fancy match statements and stuff. And here I don't need any of that, right? The only thing I'm ever going to do apparently with this salad is print a description of it. And for that I shouldn't really have to write any matches. Right now I don't have to write any matches. Well, here's the trait salad, which is a terrible name, but now the veggies are not going to be just a vec of veggies. They're going to be a vec of boxed vegetable. Oh, that innocuous little construct needs a little thinking and attention. What is a box again? Use boxes much. Somebody's going to use box against Notion. It's like malloc for Rust, right? It says, we're gonna go ahead and malloc some storage, we're gonna have some malloc storage associated with each vegetable. Why? Because it turns out the way we make these trait objects is they're a kind of smart pointer. They contain a pointer to the thing, they also contain an associated thing that says what kind of thing it is. Technically what they contain is a pointer to the V table, right? They contain two pointers. One to the actual value, and then the other to a pointer of to a pointer to a table of all the methods that you can call on that value so that you can actually have it called at runtime. Yeah.
So the book mentioned that Rust's implementation of the V table is slightly smaller than C++'s. Does that imply that C++ tags the V table on every object that you allocate?
Try to remember how C++ object representation works. The basic idea is that there's only one V table created, yes, ever for a particular type. And so even if you have multiple objects of that type, they don't, blah, blah, blah. Yeah. And so it's being a little clever about how it does it, yes. And I don't remember the details off the top of my head, to be honest. There is a clever thing it does that it can do because these aren't objects, because I'm never going to have virtual method calls here. The only thing I have is trait method calls, and it can resolve those statically. So cool. So now I box those up so that I have a vector really of smart pointers to vegetable objects. And now my implementation is going to be a little different too. I'm going to say, well, notice that there's no generic types in my implementation of trait salad. There's no capital T's floating around anywhere, yeah? Instead, I'm going to say, well, to make a new one, we make a new vector of veggies. That doesn't change at all. To add things here, I need a boxed vegetable to push into